Okay, so section 2.2 deals with the things that make the rate of a reaction occur faster. And we're going to take a look at the warm-up because it's really insightful. So here we've got 3 different beakers with 3 different variations of solid marble, which is calcium carbonate inside of it. Powder, small chunks, and large pieces. Which one appears to react faster? The powder. Okay, so the powder, anytime you have a solid, ideally you want to crush it into a fine powder because a powder will have more surface area. So that means we have more points of contact with the other reactant, which in this case is hydrochloric acid. So there are more places for the hydrochloric acid to touch the marble, and therefore your chemical reaction will occur quicker. Okay? If you take a look at B, in B, we've got some glow sticks. You know that if you break the capsule in the glow stick, you're going to get a chemical reaction that produces a glowing light. Which one of the scenarios appears to produce the fastest reaction? Yeah, hot water. So that means if you increase the temperature, you should increase the reaction rate because an increase in temperature will cause the particles to move faster. They will have more kinetic energy. They will collide with each other more often, and they will hit each other with more force, which should meet the activation energy and produce product. Okay, let's take a look at C. In C, we've got 3 different alkali metals: lithium, sodium, and potassium. They react with water to form hydrogen gas, and they form a basic solution. They also release a bunch of heat. Which one of these appears to react the fastest? Potassium. Yeah. Any ideas why potassium would react the fastest? It's related to periodic trends.
Most metallic trends.
It is the most metallic. What else? Give me some, think of a couple other periodic trends.
It's bigger.
It's a bigger atom. Okay, so this would be the largest atomic radius out of the 3. So if you were looking at lithium, lithium has got N equals 1, N equals 2. Sodium has got N equals 1, 2, 3. Potassium has got 1, 2, 3, 4. What does that tell you about the electron in the valence shell? Is it feeling the nuclear charge very well? No. Okay. So this one is the most reactive because its valence electron is furthest from the nucleus. It will readily give it up. Like, goodbye, right? It's not being held on tightly by the nucleus because it's so far away. So that's one of the reasons. Also, ionization energy. Ionization energy increases in which direction?
Up and to the right.
Up and to the right. So which one of these has the lowest ionization energy?
Potassium.
So yeah, this would have the lowest ionization energy. And that means it requires the least amount of energy to remove that one valence electron. Also a reason why it reacts the fastest. Okay? Let's turn to the next page. We're pretty much just going to be summarizing things that we talked about in the warm-up through this section. It's going to go fast. Okay? So on the next page, they talk about the factors that affect the reaction rate, surface area, which we covered, concentration, so the higher the concentration of reactants, the more collisions should occur, the faster the rate should happen, and the temperature. They can all be changed to influence how quickly we produce product. A lot of chemical reactions are carried out in with reactants that have multiple states of matter. So when reactants are present in different states of matter, we say that the reaction is heterogeneous. Usually for you, it will involve a solid with a solution or a solid with a gas. Okay? So that means in heterogeneous reactions, you want the reactants to come into contact as much as possible. And the best way to do that would be to have your solid be in powder form. So here they're showing you that if you keep cutting the surface area of a solid into smaller and smaller pieces, you're going to end up increasing the rate of the heterogeneous reaction because there will be more points of contact between the two reactants. Now, let's take a look at concentration. Here on the left-hand side in this beaker, let's say that we've got a 1 molar solution, okay? On the right side, let's say this is 2 molar. So that means we doubled the concentration. So we should have a faster reaction rate in the concentration that's doubled because the particles will come into contact more, they will collide, and it will produce product faster, okay? If we're talking about a gas sample that's a mixture of different gaseous reactants, if you increase the number of gas particles in the same container, we will often refer to it as increasing the partial pressures of the gases that are in that mixture or reaction mixture, okay? So anytime we're talking about partial pressures, we are talking about a gaseous reaction. And let's take a look at the next page so we can see how this is done. 2 different ways that this is done. A has got a lower partial pressure than B, okay? The other way to increase the partial pressure of gases would be to have a movable piston. So here, this piston has moved down, and this has caused an increase, a decrease in the volume of the gaseous reaction mixture, and then this has caused an increase in the partial pressure of the gas that we have present. Okay? So with your syringe that we used for the gas law lab, moving the plunger in the syringe up and down was similar to moving a piston up and down, okay? Okay, so increasing the concentration of solute in a solution or increasing the partial pressure of a gas will increase the rate of a chemical reaction because those particles will collide more often and they will produce product faster, okay? Now, if you're trying to increase the concentration of a pure solid or pure liquid, it can't be done. So make sure you're checking the state of matter on a chemical reaction. If you're dealing with like pure carbon, for example, and it says a little S in the lower right-hand side, or you've got some pure liquid, just be careful with that. The other thing that you have to be careful with is you cannot cut a liquid or a gas into smaller pieces. You could spread a liquid onto a larger surface area if you changed its container. So what I would do is I would change the container from, let's say, if you've got some narrow container, which is kind of like a vase. Let's say if you have something like this versus if you have something like this. If you have a liquid in this, this is a very small surface area that's exposed, as opposed to something in a petri dish would be a much larger surface area exposed, and that would allow this to react faster because there would be more points of contact, okay? And then finally, let's talk about temperature. If you double the temperature, you double the kinetic energy, as long as you're in Kelvin, okay? So increasing the temperature will cause your reactants to hit more often, and it will also cause them to hit with more energy, which means you should obtain the activation energy more often. So since they hit each other more often and with more force, temperature is the most significant factor that affects the reaction rate. Here they're showing you the difference between a low temperature versus a high temperature. You can see that when you're at this lower temperature, this is how many particles in a sample would be able to meet the activation energy versus the higher temperature. Look at how many more particles would collide with enough energy to meet the activation energy and produce product. Significant, okay? Let's take a look at the next page. Generally speaking, if you've got a reaction and you're going to increase its temperature by 10 degrees Celsius, you will double the reaction rate. This is true for a lot of reactions that occur at room temperature. Okay? Let's talk about the nature of reactants. The state of matter and the chemical structure of a substance will influence how quickly it reacts. So let's come down here and let's take a look at monoatomic versus polyatomic ions. Here on the left-hand side, I've got a silver ion and chloride ion in solution. These are monoatomic ions, which are considered to be very simple structures. And notice they're also in solution. So that means they are dissolved in water. So they are aqueous. This is a very fast reaction rate because of their state of matter, because they're dissolved in water, and because they're very simple structures. This is the precipitate that forms when you mix the two solutions that contain those two ions. It's extremely fast. On the other hand, on the right-hand side, you guys have got more complicated structures. You still have your silver ion, but then you've got your polyatomic ion, which is the acetate ion. Acetate ion is a very complicated structure. You're going to have to break some bonds there in order to get it to sort of like react with the silver. You can see how the precipitate is slowly forming in the solution as you mix the two together. Okay, so this is a very slow reaction in comparison to this one, which is a very fast reaction. Although I compare them and say one is slow and one is fast, simply by the basis of a polyatomic and two monoatomic ions, when you're at room temperature, the rate of a chemical reaction follows this general format. Anytime you have reactants dissolved in water, they tend to be the fastest that react. You would only need to compare the monoatomic and polyatomic ions if they were present, okay? Then after that, gaseous reactions happen second in line, the fastest, and then liquids and then solids react the slowest, okay? Okay, let's take a look at the last page and talk about catalysts. So catalysts increase the rate of chemical reactions without being used up. Sometimes you're going to see the chemical formula for a catalyst written above the arrow between the reactants and products, okay? And what happens is catalysts are consumed during one step, and then they're kicked out at a later step. Let me stop this for a second.